Yes.
Thanks. Okay, then I guess we can start. Uh, so I will first start and I will present what fractional differencing is. I'll speak about the theory. And then, I don't know, Jan, do you have any interesting things to show us after that?
Yeah, I could show like this DA divergence thing that I did for the differencing.
Okay, awesome.
Maybe that's interesting.
Okay, so yeah, I've also going to talk about some basic things. Maybe a lot of you know them, but maybe some of them don't. So it's and I learned a lot of those things now. So maybe it's useful to say something. So I'll first say a little bit about stationary time series, and then what is differencing, and then what is fractional differencing, and then we'll see some examples. Okay, so first, one definition, so stochastic process. This is a family of random variables indexed by time. The idea is in a deterministic process, you know exactly what happens in any given moment. So if you have some metric based on this process, then at any moment you know exactly what the value of this metric is supposed to be. But in a stochastic process, we have some uncertainty. So there we model such processes using random variables. And okay, one very simple example, this is called white noise. So we have for every timestamp t, the random variable is some variable which is normally distributed with mean or average value of 0 and standard deviation of 1. Okay, so this is an example of this stochastic process. So here I draw one sample. So here I have 1000 timestamps, and from each timestamp I draw one sample and then I plot it, and this is what you get. I can draw many samples. So for example, okay, here you see a different sample, here another sample, and so on. So from one stochastic process you can draw many samples. Okay, here's another example of stochastic process. So each variable for each timestamp t, we just take the value of this process at the previous timestamp, and then we add some random noise, which is again normally distributed. This is called a random walk. And this is how it looks. Again, for 1000 timestamps. And this is one sample, but again, we can draw many samples, and you can see that unlike the previous process, basically all the samples look similar. But for this process, every sample that we can draw is very different from the previous one. So you see here, or some other samples. Yeah, basically it can be very, very different. Yeah, so this is just one note. So if we have a stochastic process defined like this, we can draw many samples. But in reality, we use time series data, and each time series gives us only one sample, only one value for each time. But still, we often imagine that our time series is one sample which is drawn from some underlying stochastic process, and we want to understand the properties of this process. Okay. So a stochastic process is called strongly stationary if for any tau, the joint distribution of a subset of variables is invariant under translation by tau. So basically you get a bunch of timestamps, you get the variables associated with those timestamps, and what we're saying is that we want the distribution of those variables to be the same if I translate all the timestamps by a constant. So this is, yeah, very strong statement actually, but it's useful. So processes that are stationary can be. There are many statistical methods that work better on them. And there are other definitions of stationarity, but so there's no need to talk too much about that. So just to give you an idea. So let's look at our two examples. So the first example was the random noise. And basically, every variable there has the same distribution. So if you take n timestamps, then the joint distribution of the associated variables is the same, and if you translate the timestamps, nothing changes. So it is strongly stationary. And also, if you remember the graph, it's like intuitively what the word stationary means. Yeah, if you look at the graph, yeah, this process looks kind of stationary. It doesn't move too much. But the random walk is not stationary. So how can we see this? Well, so if we apply the formula, y at timestamp t is equal to y at timestamp t minus 1 plus some noise. And then y at timestamp t plus 1 is equal to y at t plus noise, but this is equal to y at t minus 1 plus adding noise 2 times. So basically, if you look at the two variables, the second one has more noise than the first one. So the standard deviation of the distribution of the second variable will be larger than the standard deviation of the first distribution. So they're not the same. So here you see that we have only one timestamp. We translate it by 1. So here tau is 1. And we get a different distribution. So this is not stationary. By the way, if anyone has any questions, please be free to ask at any time. Okay. And so being stationary is nice. For machine learning purposes, it is easier to train apparently algorithms on stationary data to do, for example, regressions or more complicated things. But in practice, in the real world, many time series do not look to be stationary. And we have some methods how to make a non-stationary data into some stationary data. And one method is called differencing. I think there are also other methods, but I don't know them. So, and I'll talk about just this one. Okay. So what is differencing? Actually, we've done this probably many times already. You take a certain, if you can think of it if you want a stochastic process or a time series, and you construct another time series or a process, and this is the process of the differences of the consecutive differences of the first time series. So I can define an operator D, which given some process X, it gives me another process dx, and the value of dx at the timestamp t is simply the value of x at timestamp t minus the value of x at timestamp t minus 1. This is the differencing operator. Okay, let's look at our examples. It is not difficult to see that if you apply the differencing on the random walk, we will get random noise. Just look at the formula, like yt minus 1 is precisely normally distributed random noise. Here there is one thing that we can notice. The random walk was not stationary, but now the random noise, so when we apply differencing to these ones, we get a stationary process. And apparently this pattern works in general. So if we have a non-stationary process, we can apply differencing and we can make it more stationary. Sometimes we might need to apply differencing more than once. So here, let's say that we have some process x, and then we apply differencing once and we get dx, and we can again apply differencing on this other process, we get another thing, which is d squared x. And so here you can see the formula, how to see what is the value at a given timestamp of d squared x. One can derive it. In this case, it is x at timestamp t minus 2 times x at t minus 1 plus x at t minus 2. And we can continue, so we can apply it n times consecutively. But there is a problem. And this differencing operator loses information. And we can see this best when we look at price. If you take the log prices and we apply this differencing operator, we will get the log returns. And log returns look to be more or less stationary. And the log price is not stationary. So this operator works. But there is a problem. So we have lost some of the information that was contained in the price. For example, if you have log returns of or returns of 2%, you could have the same 2% in, let's say, 2012 and 2019. So it's the same number. But if you look at the prices, well, the value of the, for example, Bitcoin, the price of Bitcoin of 2012 and the value in 2019, they were just completely different values. And so in this value of the price, we have some information about the fact that the market is different. And there are some different things that have happened, and they're reflected in the price in 2019. But if you just look at the log returns for one day, you don't see this information. And if we want to be good traders, so the job of a trader is to turn information into money. So if we lose information, that's not good for business. And now we have this one idea how we can achieve some kind of a compromise. The idea is we want to extend this differencing operator to be able to apply it a fractional amount of times. So I showed you how we can apply it once, twice, 3 times. So this is a positive integer. But we want to now be able to apply it, let's say, 1/2 times or 0.1 times. And then the idea is that if we can do this, then maybe we can find some values of this power or order d less than 1, where the resulting time series it's still kind of stationary, but at the same time we have not lost so much information as we do when we take d equals to 1. So we can reach some compromise in this way. So let's see how we can do that. Now, do you have any questions so far?
No question, just if it's possible. Well, generally it's understandable, but few charts, it's always visuals, easy to follow up.
Sure. I'll show you.
Or they will come later.
Yeah. There are charts, no problem.
Okay.
Also, one important note that stationarity comes from econometrics, but not machine learning field. So most of machine learning, they don't need the data to be stationary.
Well,
in econometrics, that's a really strong condition, but not in machine learning.
My intuition is, from what I'm seeing, like for this very simple case of linear regression, even, it seems to me that the linear regression will perform better if the data is stationary than if it is not.
Yeah, but it comes from econometrics, the pure linear regression. So that's very important to have stationarity for regression.
Yeah. But still, like the same, if you have a more complicated machine learning model, I would guess that the same reason why it's good for linear regression to have stationary data, the same reason should apply for more complicated data as well.
Tree-based models doesn't require stationarity, and neural nets doesn't require it. So it depends.
Okay.
And also, you told about strong stationarity, but I also know that there is a weak stationarity, and in practice, it's enough to have weak stationary time series.
Yeah.
Is it right or?
Yeah, this is just this was the strongest definition that I showed here. Weak stationarity means just to have the mean should be constant, and there is one other condition.
Standard deviation should be constant.
It's not the standard deviation exactly. It's a certain. Anyway, we can look at it later. It's not just the number. It's you still look at how the variables relate to each other. So I think there was some matrix that you have to be you want to be constant.
Okay.
Yeah.
Maybe just also like for the intuition, like I think what helps is like if you think about a variable that you want to use to predict price, for example, if you have a sentiment score that is between 0 and 10, for example, and it learns basically what a regression would learn is like this value of 0 to 10 multiplied by something gives me the price. And like if the price in the end is, I don't know, 10,000, we can see like if the sentiment is very high, is at 10, we multiply that by 1,000 and can end up at 10,000, for example. But the price can then, of course, still go higher. And that's something that this model could then not incorporate, because the maximum it could ever output according to these learning parameters would be 10,000 in this case. Unless, and this is where this idea of co-integration comes into, unless this predictor variable, like sentiment in this case, can grow as well. So if this predictor variable grows together with the price, for example, then this could work. And this is actually why in econometrics, as Alex said, you typically want to have stationarity unless you have this co-integration, which also Plan B with this stock-to-flow model refers to, basically. Just
Yeah. Okay. Yeah. I mean, I think most of the people that are listening to this forum, this talk, know more than me. But anyway, uh, so yeah, let me now show you how we can define this fractional differencing operator. We have our initial data, so some time series, for example, but we have finite data points. And so we can put all of those finite data points in a vector. So here it's x, a column vector x1 to xn. And then we define a certain matrix here. It's 0 everywhere except on the diagonal under the main diagonal. There you have ones. What this matrix does on the data, it just, you imagine it translates to the right all the entries, and it puts a 0 at the first place of the vector x. So when you apply this matrix B on x, at the first place you get 0, then at second place you get x1, and third place you get x2, and so on. So the differencing operator, I can express it as this formula. So if I put I to be the identity matrix, then I minus B applied to this vector x will exactly give me the difference. So at the first place, I don't have a previous value, so I'll just retain x1. Then at the second place, I'll have x1 minus the translation, which is, on second place, I have x2 minus the translation, which is x1. Then on third place, I have x3 minus x2, and so on. And if I want to apply this differencing operator more than once, this is the same as taking this matrix A minus B and multiplying it many times. So this was for integer values of D. But how can we now define it for fractional values of D? Well, it turns out that we can. So I can use one formula from high school. For integer values, I can uncover the brackets. So d to the power of d, this is I minus b to the power of d. Then I uncover the brackets and I write, there's this binomial coefficients that we get. So in the end, I can express d to the power of d as a sum of powers of this matrix B times some coefficient and some weights. And where you can see what the formula for the weights is on this slide. Notice the following important part. So here we assume that D was positive integer, right? However, if you look at the formula for the weight, so this minus 1 to the k times a product of some things. So, well, here D doesn't have to be an integer at all. So you can put any value of D there, and this formula will be still okay. So it is well defined. And another thing that you should notice, for if D is an integer and k is larger than D, it's not difficult to see that those weights are actually 0. So this sum that I wrote, sum of k from 0 to d times the weights times this matrix B to the power of k, well, I can actually replace it with an infinite sum, because for very big values of k, the weights will just be 0, so it's the same thing. Okay, and so this is what I've done here. So I can just replace the formula that I had in the previous slide with this formula. So d to the power of d is an infinite sum of the weights times b to the k. This is still, we assume that d was a positive integer, right? But now let's look at this formula. Well, the thing on the right, it is completely well defined, it turns out, even if d is a fractional number. So this is a power series, and we have to prove that it converges, but that's just details, it does. So actually, we can use this formula as the definition of what it means to apply this differencing operator a fractional amount of times. That's the main idea. Did you understand?
Could you repeat once again? What is K? That doesn't rank of the matrix.
K is a number. K, you just raise a matrix to a power K. You just multiply the matrix K times by itself.
Okay, and how do you choose K? In general case or?
Here you don't choose K. Here you see a sum.
Okay.
So
I get this.
this is a like a power series with some coefficients and a matrix. That's the definition.
Okay.
And as I said, we can prove that it converges, but actually in this case, it's very easy to prove that it converges because this matrix B, if we raise it to a power of n, so n was the number of entries of this vector x of data that we have. So if we raise this matrix B to the power of n, you will get zero, the zero matrix. So maybe, let's see, let's go back to the definition of the matrix. Yeah. So basically raising this matrix B to some power, it means if you compute it, you'll see that what will happen is that this diagonal under the main diagonal, it will start moving down. So if you raise it to the second power, the result will be, well, you have, so this diagonal will become 0, and then the next diagonal will become equal to 1. And so on. So if you raise it to a high enough power, this matrix will simply be equal to 0. So for any fixed number of data points, fixed number of timestamps, this infinite power infinite series is not infinite, it is finite. But still, it's not very smart to compute all the weights. So right now from this formula, you actually see how we can compute this differencing. So we have to compute those weights, which I showed in the previous slides. So those weights, we just have to compute them, and then we have to compute this resulting matrix, which we have. And once we have the matrix, we just apply it on the original data, and this is how we get the result. But we don't really need to compute all the weights, so this is can be computationally intensive, and there are some other numerical problems. Instead, we can just compute an approximation, and one approximation which we do here and which is in the book by Prado is the following. So the weights, they converge to 0. So we can just pick some threshold tau and then compute weights up to start computing them and just stop when we get a weight which is less than tau. So they also their absolute value goes monotonically, converges to 0. So that's that will work. And with this approximation, we don't really have to compute all the weights. So you can imagine, for example, if you have some metric with 10,000 timestamps, you don't really need to compute 10,000 weights. You can just compute a small number depending on how precise you want your computation to be. Okay, so now let's look at one example. So this is how you can get this functionality. I've implemented the fractional differencing, and right now it is a PR in the Quant Garage repo. It will get merged, and then sometime next week it will also be on Data Lab, so you can use it yourself. Okay, so here we get Bitcoin, price, and mean age. And then I don't really work with the price itself, but with the logarithmic price, because it seems to be better suited for this operation. And now we're going to make one test to see at what level of D do we get a sufficient level of stationarity. This is the so-called augmented Dickey-Fuller test. So this is what was recommended in the book. And I couldn't really understand it in detail, how it works. It seems that if you want to understand it, you have to read the original papers. So the information that I found on Wikipedia, it didn't seem, at least to me, sufficient. So this is how this test works. Here we get, you see a table with the results, and I will explain what this table means. The first column, this is the level of differencing. So here we're differencing from 0 to 1. 0 means no differencing at all. 1 means just the normal, we apply the normal differencing one time. So we apply this differencing on our data, and we get some time series. And then we apply this test on this time series. And we get a number. This is ADF stat. And then there is a certain confidence interval, which is part of the test. And so the idea is that the more negative this number is, the more probable it is that the time series is stationary. And we have to look at, we have to compare it with this confidence interval. So here, if the statistic is less than the confidence number, then, okay, the test tells us, okay, this looks to be stationary. So here, actually, even at 0, they seem to be pretty close. So the test would say that, yeah, this is okay, but actually it's not. I mean, the logarithmic prices, they're not that stationary. But yeah, when you apply a logarithm, I think that's another way to make things more stationary. So maybe that's why this test gives us this result at this point. If you go down, so if you start to increase D, you get much lower values. So we are much more, it seems to be much more stationary, let's say. I will show you right now what this means. So here, for example, we can pick this value, 0.4. It seems to be pretty stationary compared to the benchmark number. And then on the right side, you see a correlation between the original time series and then the resulting time series, the fractional differencing, the time series that you get by fractional differencing. So from the original, when we don't apply any differencing, they're fully correlated, so correlation is 1. Here, when we apply differencing at level 1, so when we get the log returns, there is basically no correlation. And see, what this means is that the logarithmic price and the logarithmic returns are not correlated at all. So basically, a lot of the information, all of the information, all of the memory that was contained in the logarithmic price, it is erased when you compute the returns. But at some middle levels, you can see that we can get some compromise, right? So for example, for this 0.4, the statistic seems to be pretty negative. And at the same time, the resulting time series still looks to be somewhat correlated with the original time series. So it still contains some of the original information. Okay, so here is how we can compute the fractional differencing time series with the methods that I've written in the quant garage. So here in the first example, you compute it for level 0.4. On the second, we compute it for level 1. So here we get, this is one function which computes the weights first. No, so this function computes the weights first. And then we use the weights to compute the final result. And here you can see the values. And then, okay, so here is a graph. So this is what things look like. The blue one is the original log price. The green graph is the log returns, logarithmic returns, and it is kind of stationary, right? So it doesn't move too far, unlike the price. And the orange line is what you get at level 0.4. And here you see that it looks to be kind of close to the returns, so it is somewhat stationary. But at the same time, it still contains some of the information that was also that is contained in the original logarithmic price. Okay, and now let's do the same for mean age. We can do a search again and see what are the different, what does the statistic tells us. So, for example, you can look at 0.5. The ADF statistic is less than the confidence, and at the same time we have a still we have a time series which is correlated with the original mean age. So we can apply here also the this method. And this is the result. The blue one is the original mean age. The red graph is the normal differences, daily differences of the mean age. And then you see for 0.5, the green graph, this is what the statistic tells us that it should be pretty okay. And yeah, it seems to be pretty close to the to the case when the order of differencing is 1. And then I also plotted here some another metric in between. So for d equals to 0.2, so this is, you see, not so stationary, but it still seems to be more stationary than the original time series. Okay, so that's from me. So this is the where I got the information. This is the chapter 5 from the machine learning book. And I've used some code from this library MLFinLab, but I had to rewrite it. And now the code is in a PR in the Quant Garage. So thanks. Do you have any questions? Or maybe we can continue with something that Jan can show more interesting?
Tzanko, thanks. Even me understood something. It's good work you did. How do you see application in what we've been doing lately? Because I was trying to say, how can I apply? For me, it's difficult yet.
Yeah.
And it's mostly because simply it's too new for me. So you've been thinking about it for some time. So I
see several places, but maybe we can see what Jan has. But I see several places where we can apply that. One is for the anomalies. that Irina was working on. I think, Irina, when you are looking at the time series, you probably notice that in some cases, for some metrics, you have to apply some differencing to get, So this is one place where we can use it. Another place.
Okay, yeah, makes sense.
Another place is, for example, well, we've used linear regressions in several places. For example, in the fundamental model, so this divergence, the DA price divergence. It seems that in general, if we are going to use any statistical methods, as Alex said, it doesn't. This is not necessary for all methods, but for some of the methods, we will have to first apply differencing of the metrics and then apply the method, and hopefully we will get better results in this way. But I don't know. Initially, I didn't really have much time for this, but I'll be really curious to see what will happen to the fundamental model if we apply this differencing thing. Yeah.
I would suggest to deploy into strategies fundamental model and fundamental model based on fractional differencing and see how they behave in live tests, so we can measure. I think it would be fine at least.
Yeah, we can do that. First, we have to see if it actually brings any benefits with historical data, but if it does, yeah.
Mm-hmm.
Okay. So if there are no more questions, maybe Jan, you can show something more interesting.
Yeah, so what I just wanted to show or to talk about, let me share the screen. Okay, so what I was thinking of using it for is, as we said, like this DAA divergence research. It's not really machine learning or modeling related. It's actually something different, because what we do in the typical DAA divergence, I don't know if everyone knows about this. The idea is basically you look at the price of, in this case, Bitcoin, and at the daily active addresses, and then you look for instances or situations where the price goes in the opposite direction, strongly in the opposite direction of daily active addresses. And we've seen that a lot of the time this is a good indicator for a trend reversal, and can even produce the buy and sell signals, basically. The problem I had with this general methodology is that it's relatively like the question of how do we define the trend, and how do we define the threshold, like what kind of difference in trend between daily active addresses and price do we see as a signal. Those are relatively arbitrary, actually. Like you just select, I selected an arbitrary method. In this case, I looked at the sum over the log returns, and I had to select an arbitrary window, basically, over which I calculated this trend, basically. And then I have to select basically a more or less arbitrary threshold on top of that, like what counts as a strong enough divergence to fire a signal. And what I was thinking was, or what I was trying out was this, to do this with the fractional differencing, actually, because what I thought was a cool idea is that it's this fractional differencing is kind of has memory. It shows some form of trend, and it basically continuously, as far as I understand it, it continuously, like the information degrades the longer you back. So this kind of gets rid of this problem that we have with you have to select a certain time window where you specify like what kind of window do you look for this trend and stuff. So what I did instead was basically to just take the fractional differences over price and daily active addresses, and then compare this basically. And then the only parameter that you basically need to select is, as Tzanko said, this this D value of like how much history do you want to have in that. And in this case, it's at least it's not completely arbitrary, but it actually has some. We know how we could find this value basically, in the sense that we want to look for something that is still stationary, but does not but contains as much information as possible. So there is a way to find this parameter basically. In this case, I basically what I then do is standardize the metrics, because these tend to be like in weird ranges. So I basically just standardized the values and then looked at the difference. And what the standardization also means is that it's like it's rescaled to center around 0 with a standard deviation of 1. So the threshold as well that we define now, I mean, we still have to set a threshold. But the cool thing is that it's like with this standardization on top of that, we do not, it at least makes some sense that we can talk in terms of have a standard deviation of 2 or a standard deviation of 3 as a threshold. So this works also to make it kind of, I think, more theory-based or something like that. So we actually come from somewhere when we select these parameters. And yeah, then you can basically do the same thing and get some signals as well. So in terms of how they work or how well they work, we can see here for like these are the signals in this case for a specific threshold of 3 standard deviations. And yeah, I mean, like they still do kind of work pretty well. So you would be a buy and then you sell up here and then you buy here. Well, you don't sell here, but here also like the buy signal is pretty good. And the event study would also tell us that after the buy signal, we typically have an upside of around, I don't know, like 10%, which is of course only for 6 signals in this case. But yeah, so does it work? Here we have like, this is the normal DA divergence signals. Here we also have some so yeah, even maybe a bit stronger. So but I also have to see like how to specify this more precise. So in this case, I don't do the log, the fractional differencing of the log. I think I didn't do that yet. So there's some stuff to specify. Yep. Yeah. So in the end, basically, does it work better? Definitely, I can't say that yet. But I think what makes sense to me is that this method does not need so many arbitrarily specified parameters, but we actually can find the parameters that we have. We can kind of reason on why we chose them that way. Yeah, that's the idea. Any questions?
So you are running event study on the events, but there are
Yes.
very few events, I would say.
Yeah.
So why didn't you make more events out of this data? I mean, why didn't you like lower the thresholds for the signal so you have signals?
Yeah, like maybe that's intuition out of like the way we did it here. The thing is, of course, like these are pretty good signals so far. If we lower the threshold, we fire a lot more, and then the question is, are these signals valid in a way? That's always kind of the trade-off, right? Like so you can, of course, do more events, but then the question is, are these still good if you constantly fire? Does it work for lower frequencies and stuff? You're right. I should definitely try that, especially with the event study that is basically designed to try it with more events. But yeah, like, definitely need to do that.
Mm-hmm. Yeah, because like take signals for about 3 years. That's not a
Yeah.
lot.
In this case, it's not. Also, like the strange thing here is we don't really have any signals here. I also need to check what was going on there. Why didn't it fire at all?
Yeah, because with this nice module, we can take any threshold and easily test it.
Yeah. Yeah, of course. Question is, maybe I can do this. Let me see if this works or if it breaks. Yep.
Okay. So one thing that you still don't have early results. For the module, the threshold that you put there, the way it works is it gets rid of the initial result of the fractional differencing operator, because the initial data, it's based on a smaller set of so if you take the result at early timestamps, well, it is based on less data from the original time series than if you take the result at later timestamps, and that's why one traditional operation is to get rid of the early data. And if you have a very small threshold in the fractional differencing parameters, then you get a lot of weights, and then this also means that you get a lot of early data will be just deleted. If you have 100 weights which are non-zero, then the first 100 entries will be deleted. So I have just copied what is in the book. I've copied this functionality. So it's also possible to not have this functionality. I think in the graphs that I showed you, I have this turned off. And there you can see how initially the data looks a little weird. Let me show. Okay. Can you see now?
Yes.
Yeah. Okay. Yeah, I cannot zoom very well, but maybe you can see how in the initial values of the differencing look a little bit different. So let's see what will happen if I increase the decrease the threshold. Yeah, I don't know if you can see this. there's this initial here drop, and on both differencing so values, which this is just an artifact from the fact that initially we don't have enough data to compute the differencing. So here you actually need some data from the past years, and we don't have it, so that's why we the data can be a little bit weird. And in the original method, some of the initial data is cut off because of that. So that might be one reason why Jan doesn't have early data in his graphs.
Makes sense. Makes sense.
Yeah, also I like the idea of dropping the earliest data because the market was quite different. And I think it was really different. So that's more than fine.
Okay. I guess that's it for today. Does anyone have any other questions or comments?
I have a question. When you compute this threshold for the weights, I mean, when you choose it arbitrary, are there any rules to choose it, or it's constant for? It's more or less the same for any data.
I think it's not very difficult to choose it. Basically, what I looked at, I looked at the following: how many non-zero weights do you get? And if you have too many non-zero weights in comparison to how much data you have, then that's not good. It doesn't make sense to have such a big threshold. So then you can reduce it. So I think for 10 to the minus 5, the weights were, for example, for the lock price, you had more than 3,000 for sure. So maybe, I don't know, several thousand non-zero weights, but we had only 3,700 data points for daily prices. So actually, in that case, you had more weights than data points. And in that case, if we apply the original algorithm to drop the early data, well, that would actually drop all the data. So yeah, if you increase the threshold, then you get a smaller amount of weights. This means that the result of the at a given timestamp depends on shorter history. So basically, if you have 50 weights, essentially this means that the result at a given timestamp depends on the past 50 days. And yeah, so it depends on how much data you get, I guess.
So it's better to test different thresholds and to choose the best one.
Yeah, I just chose. I looked at the 0.1. I think in the book he uses just 0.1. The default value in the in ML FinLab is 1 to the minus 5. Sorry, yeah, you know what I mean. 10 to the minus 5. Here I used 10 to the minus 4. I think in most cases, which seemed okay for the amount of data that we have. But I guess if you have hourly data points, you can afford bigger threshold, a smaller threshold.
Okay.
Yeah. Okay. So yeah, I guess we're finished for today. Thank you, everyone. I don't think that we have a talk for next week, unless anyone wants to show anything. So for now, I guess next week's seminar will be will not take place. And then later we'll see, I will look at the chapter for structural breaks, and once I understand it, I can explain what it says also. Yeah. Okay, so thank you, and yeah,
you.
have a
Yeah,
nice
thank
day.
you.
Bye-bye.
Thank
Yeah.
you. Tzanko,
Same.
could you
Thank
stay
you.
for a few minutes?
Oh, okay.
Yeah, so I have one